Okay, now let's look at briefly the issue of so-called complex waves. In other words, we're not just looking at a harmonic wave, sine and cosine wave. Okay, a complex wave, which is not necessarily simple harmonic anymore. We have a complex wave, but we still want to make sure the wave is periodic, which means it does repeat itself. It's not a sine or cosine function anymore. The idea here is that even though the wave is not harmonic, okay, it's not simple harmonic, what we can do is use what's called Fourier analysis. Okay, that's attributed to the French mathematician Fourier. What is Fourier analysis? A Fourier analysis takes any periodic function. Here's a periodic function, okay? The period is t, all right? Given that period, you can find the corresponding frequency, f, which is 1 over t. Okay, this is called f1. We call it the fundamental frequency. And then we can define f2, f3, f4, and so on, which is 2f1, 3f1, 4f1, and so on. Okay, so the idea is this. Here is a periodic wave with a fundamental frequency of 1 over t. Okay, if I use a simple harmonic wave, I'm not going to be able to use that simple harmonic wave to totally mimic the original wave, because the original wave is not simple harmonic. However, according to the Fourier analysis, even though a single harmonic wave is not going to do the job, what I can do is to use a whole bunch of simple harmonic waves. See, take a look. This is the sum of a whole bunch of simple harmonic terms, right? Look at the first term here, a1. Here's 2 pi f1t sine function. Here's 2 pi f1t cosine function. So it can both be sine and cosine. Okay, so here I'm using a sine or cosine wave at the frequency f1 to mimic it. And that is not enough, so I add another wave with a frequency f2, both sine and cosine, and then f3, both sine and cosine, and so on. Turns out that for any complicated periodic wave of this period t, if I choose a sub n and b sub n wisely, appropriately, I can always use these sine or cosine waves to represent any of these waves. Okay, in other words, if I choose a1, a2, a3, a4 correctly, all right, I can use these sine cosine waves to exactly represent any non-harmonic but periodic wave. Now, why is this important? Because periodic waves are because simple harmonic waves are simple to study, but they're boring, especially when it comes to music. Here is a drawing for a simple harmonic wave like this. Okay, it's got a certain period, okay, from here to there. It's got a certain period t, of course, corresponds to a certain frequency, f1. Okay, if a wave behaves like that over time, when you hear this wave, it's not going to be very musical. It sounds like what? Like a tuning fork. Okay, a tuning fork is designed to produce only one frequency. Okay, it doesn't sound terribly good. Now, here I have a different type of wave. It has the same period as that one. Okay, same period. I mean, I didn't draw it very well, but my intention is to draw the same period as this one. But you see, the form is not simple harmonic anymore. There are some wiggles here. Okay, some wiggles here. And when you play a musical instrument which produces a wave like that, you compare this with a tuning fork at the same frequency or same period, you will find that you're playing the same tune. Okay, you're playing the same note, but it's going to sound a little different. Why? Because this wave is not simple harmonic. As a matter of fact, if you use a different musical instrument to play the exact same tune, you got to have the same exact period, but this time the waveform is again different. Okay? Even though they have the same period, these are all periodic waves, those two are non-simple harmonic and the form differs from each other. You can hear the difference. Maybe this is one piece of instrument and here is a different type of instrument that looks just different. I mean, actually, the sound just different. Okay, as a matter of fact, on page 566, you have a diagram like that. The first one is a tuning fork. This one was intended for flute, and that next one is intended for clarinet. You know, of course, if you can use flute and clarinet to play the same tune, you can still tell, okay, no, this sounds different, it sounds like a flute, and here it sounds like a clarinet. They are playing the same tune, so T is the same, okay? They're all periodic functions of the same period, but they sound different because they have different waveforms. Using Fourier analysis, I must use the same base frequency, fundamental frequency, and the higher frequencies for all of them because, again, they have the same period. Okay, but to mimic the difference between this wave and that wave, what you need to do is you have to choose A1, B1, A2, B2 differently for this wave and that wave. Okay, but as long as you do A1, B1, A2, B2, and so on correctly, you can produce a wave like this, exactly like this, and produce a wave exactly like that. Okay, so this is to say any periodic wave is always can always be represented by a whole bunch of sine and cosine, in other words, simple harmonic waves. And this procedure of breaking down any complicated periodic wave into a series of sine, cosine functions of those frequencies, it's called Fourier analysis. And each of these, each term is called a Fourier component. Okay, let's take a look at page 567 in the textbook. Using the same three waves that we studied before, tuning fork, flute, and clarinet. This time, we plot the so-called Fourier spectrum. Okay, what's a Fourier spectrum? Basically, you know, each of these non-harmonic waves is a sum of a whole bunch of sine cosine waves, right? Each one is called a Fourier component, remember? And this is the tuning fork spectrum. A spectrum means how do you break it down into different Fourier components. Okay, this is a tuning fork. And our tuning fork produces a pure sine or cosine function. So you only have one term. Okay, you only use a single harmonic term. You don't need the second, F2, F3, and F4. So therefore, you only have one line here. The sound is pure but boring. Okay, here is the flute. For the flute, you have F1, but you also mix in a little bit of F2, a little bit of F3 and 4, and so on. By the way, F2 equals 2F1, F3 equals 3F1, and so on. And if you mix them according to this kind of proportion, okay, in fact, here F2 is the largest. It's even greater in amplitude than F1. It's going to sound like a flute. Okay, now, next one is clarinet. With clarinet, playing the same tune, you're going to have the same Fourier components. You're going to have the same F1, F2, F3, and 4, so on, right? But why does it sound like a clarinet instead of a flute, even though they're playing the same tune? It's because the spectrum is different. Here, the second F2 component is rather low instead of rather high here. So the first one is pretty high, but look at the fifth one. Okay, this is F5, okay, which is 5 times the frequency of F1. It has a pretty high amplitude. So when you use simple harmonic waves, F1, F2, F3, F4, 5, and so on, mix them in with this kind of relative amplitude, it's going to sound like a clarinet. This tells us, in principle, how to make an electronic keyboard. You know the electronic keyboards, right? You can switch to different playing modes. You can mimic a piano, a violin, anything you want, right? How does the same piece of electronic instrument mimic all these different types of sounds? Well, the principle is rather straightforward, and that is you must obtain the Fourier spectrum for each of these musical instruments being played. For example, if you want the thing to sound like a flute, okay, then the first thing you have to do is to find the Fourier spectrum for a flute, and which will look briefly like this. Okay, I'm copying a diagram from the textbook on page 567. The first diagram on top, the middle one on top. Okay, so it's like this, right? This would sound like this. So here is F1, F2. Remember, for the flute, F2 is largest in amplitude, and so on. Okay, so what you do is you design a computer chip. Okay, this computer chip will mix different frequencies in at this kind of proportion. If you want this thing to sound like a flute, you want the strongest amplitude for f2, which is twice as f1, okay, and the rather strong amplitude for f4, and so on. You mix them with this kind of proportion, it's going to sound like a flute. Of course, these are 1, 2, 3, 4, 5, 6, 7. There are more, afterwards. Okay, so what is the difference between a good electronic synthesizer or a mediocre one? Well, a good one uses even more. Okay, you keep on going. So you have basically more terms from the Fourier series in order to have a more detailed representation, more faithful representation of the Fourier spectrum of the flute. But if you fully analyze the spectrum of the flute, and if you put all these frequencies in, you don't miss anything, put all of these in at the right proportion according to this diagram, it's going to sound indistinguishable from a real flute. Okay, so if you want to play, if you want to sound like a clarinet, and then what you do, you go back to the diagram of the Fourier spectrum of a clarinet. Okay, so you adjust the relative, use the same F1, F2, F3 because it's the same tune, right? But you readjust the relative amplitude of F1, F2, and so on, using that's of course controlled by the computer chip. So that is why the computer chip, using the Fourier spectrum, by mixing these frequencies in, you can produce whatever kind of musical instrument sound that you like. Okay, what we have here is also is another rather stunning example of how, using the appropriate Fourier components, you can get whatever periodic wave you want. What we have here is we added only three Fourier components. Okay, F1, F2, and F3. There are only 3 waves. Okay. Actually, I'm sorry. Let's take it back. We only have 2 waves. Okay. Here is one wave with the frequency f. Another one with frequency 3 f's. Okay, so vibrates faster like this. Now we add these 2 waves up. What we get is this red wave. Okay, this red wave. This red wave we don't recognize as anything special. But it is not harmonic anymore. Okay, it doesn't look like just smooth up and down anymore. Rather, it's up and then down, then up and down like this, right? This is the result of adding 2 waves up, one with frequency f, the other with 3f, with of course the correct amplitude. Okay, now what happens when you mix more Fourier components in? So this time I have 3 waves. Okay, I got 3 waves: f, 3f, and 5f. I added one more. Okay, I have a 5f, so this is the new one. Okay, this is the newest one with the frequency 5f. This time, by adding all these 3 up, I get this green wave, which is the result. This green wave looks kind of like the red wave, except, it stays flatter at the top, flatter at the bottom, flatter top and flatter, and goes up and down rather fast here. Guess what happens if I continue this trend? Well, this time, I'm going to add even more. 1 component, then 3f, another one, 5f, 7f, and 9f. I add 1, 2, 3, 4, 5. I add 5 Fourier components. I add them all up. Here is what I get. Look at this resultant blue curve. This blue curve is almost like a square wave. You see? So you wonder, how is it possible to use smooth sine cosine waves to get sharp edges? It turns out, yeah, you can actually do that. All you have to do is to make sure you put in the right frequency, arrange them with the right relative frequencies. Relative amplitudes. Okay? That's Fourier analysis. In fact, what you have here, you still get these wigglings, okay? It's not perfectly straight at the top and the bottom. The reason is because we only added the first 5 Fourier components. There is 1, 3, 5, 7, 9, there's 11, 13, whatever. You keep on adding, okay? You keep on adding, then you find the more waves you add, the smoother it's going to become at the top and the bottom. Eventually, you're going to get sharp edges, exactly like that. So this is a stunning example on how you can use Fourier analysis to get pretty much any periodic wave, including those very sharp edges, in other words, square waves. Okay, let's look at a sample.